I'm going to talk about the test facility for the linear colliders. There must be a lot of facilities, but I just listed several major ones. TTF at DAISY, FATB Asset, NLCT at SRAC, ATF at KK, and CTF at CERN. And I should add, I should add SLC, though it's not a really test facility, but it's the first linear collider, and we can learn a lot from this. And please note that this is not an overall review. I cannot do that, and I only say some few things for TTF and ATF. And I will say only a little bit about facilities at SRAC, because I thought next speaker will cover the R&D in the US. And I also will not talk anything about CTF, because I think it's compared with other projects, it's a future project, not a present. And I should say these people helped me to prepare my talk. Then let me start from Tesla test facility. And looks like this, and there is the cavity treatment assembly region, and the cavity testing, and cryo module assembly region. And this is the TTF Linux, which is like this. The direction is opposite from the previous figure, but here is the electron source, and basically this consists of two modules of superconducting cavities, and each module has 8 9-cell superconducting cavities. And there are undulator and bunch compressor for FEL test. And this region is a diagnostics. Okay. Okay. Basically, there are two things as challenge for Tesla cavities. I took this from SNOMAS website. So first is a high accelerating gradient, 23 megavolt per meter for the Tesla 500 and 35 for 800. And I think this was already shown by Chris on Monday. So I want to say something about pulsed operation of Tesla. Okay, what is pulse? If you want to go to the high gradient operation of superconducting cavities, you have to operate the pulsed one, not continuous, because even if the quality factor Q0 is very high, still in the if you operate continuously, you cannot the cryogenic system cannot accept the power loss. So we have to do pulse operation. Looks like this. There must be some field time, in this case 5 microseconds. Then the beam passing period, which is 800 microseconds. Then in this beam passage, you have to keep the gradient and phase constant, or you may say that you have to compensate the beam loading. Okay, so then they actually demonstrated already demonstrated the beam loading compensation by RF control. This shows that maybe energy of the beam from 0 to 800 microsecond of the, and this shows the bunch charge or the long bunch terrain. And you can see that the energy difference, bunch to bunch energy difference is very small, and I think this is smaller than the energy spread of the single bunch. So basically, you can do the beam loading compensation using the RF control. But if you want to go even higher gradient, you have to worry about the frequency detuning. Because the superconducting cavity is not rigid. It's like a mechanical spring. So if you apply a higher gradient, then the electromagnetic force will deform the cavities. It means the resonance frequency will change. And the change will be the proportional to square of the gradient. So as shown here, the change of the frequency, resonance frequency will be larger than the cavity bandwidth, which is about 300 Hz. So it means to compensate the, this detuning by only using the RF power, input power, you need to have a big overhead for the RF source. So probably it's okay for the Tesla 500, but if you go to 800, you need to compensate this. So they actually test the compensation using the piezo electric tuner. This is the end of the cavity, and changing the length here using a piezo, you can change the detuning frequency. And it was tested very successfully, shown here. This is the detuning frequency without compensation. Then they compensate this using piezo like this. So this region is the beam is here. So they could demonstrate this compensation. Okay. Let me make a kind of summary of their operation. They demonstrated high accelerating gradient, which is comparable to the Tesla 500 design. Actually, the first module operated with beam at 21 or 22 megavolt per meter. And the second one, actually it's assembled earlier, is operated about 19. But this was limited by input old designed input coupler. So new couplers are improved. So this can be improved. Then they continued operation about 10,000 hours, very stable operation, and they demonstrated production and acceleration of long bunch train with full beam loading and small bunch to bunch energy difference. Then, as I showed, detuning compensation is demonstrated. And their near future plan is like this. From now to April, they will operate with the present setup. And the last 6 weeks, they will do the full beam loading at the maximum gradient of the first module. Then in May, they will install the superstructure, so-called superstructure. Superstructure means superstructure looks like this. Usually, a normal structure has input coupler for each 9-cell cavities. Each 9-cell cavity, single 9-cell cavity. But for superstructure, it consists of 2 9-cell cavities and only 1 input coupler is here. So it can reduce the length of the length or increase the active accelerating length as compared to normal design by about 6%. So it effectively increase the gradient by 6%. So they will test this. And also second module will be replaced by another module which can be operated higher gradient. Then in October they will start installation of TTF2. It's a elongation of the present setup. So they will install another 4 modules until beginning of the next year. Then the test will be start in spring of the next year. Then they can expect to get 25 or 30 megavolt per meter for the module ACC 3 to 5. Then the last module, ACC 6, will consist of electropolished cavities, which you can expect even higher gradients. So, okay. Let me say a little about the facilities at SLAC. For FFTV, this is a little old, but this is 200-meter final focus prototype at energy of 46 GeV, and it demonstrated optics and tuning of the final focus system. And it achieved beam size about 60 nanometer, which is 1 order bigger than the present design of the NLC or JLC. But you should note that the vertical emittance was about 500 bigger than the LC design. So beta function is even smaller than our design. Then there are a lot of very important development of diagnostics. For example, beam position monitors and magnet movers. And beam-based alignment was demonstrated in microns. The component stabilization in nanometers, or beam size measurement, the size of order of nanometers by laser interferometer monitor. Now, and also it was used to test the beam-beam interaction, or now it is used to study machine protection system. ASEP it measured wake field measurement, and it demonstrated the wake field suppression by damped detuned structure. So the important thing is the calculation and the measurement agrees very well. So we can trust the calculation. then we can design the structure. And NLCTA, I think I can skip this because it's already covered by quiz on Monday, but just let me say it used presently as RF structure test facility, mainly to study the gradient limitations. And they have 8-pack plans called 8-pack to demonstrate the new or present design of RF system. And first step will be fall of this year, and full test will begin in the next year, I think. Okay, let me go to ATF at KK. This is test facility to test the production of low emittance and multi-branch beam. And there is a S-band LINAC as an injector for this damping ring. The circumference is about 140 meters. Then the beam is extracted to this line with many beam diagnostics instrumentations. Okay. Then this is some parameters of the ATF for single branch operation. And energy is a little lower than the original design and much lower than the actual design. But for particle intensity of the branch population, it's a little higher than the JLC design. And if you look at the emittances, at low intensity, we achieved the design values. But if we go to higher intensity, then we observed a very strong dependence on the intensity, and this comes from the intra-beam scattering. I will show next. And I think I should say that we don't use wigglers now. So this is very important, actually. And so the damping time is longer than required for the NLC, JLC. So we need to test this wiggler effect of the wigglers. Okay. Let me show the emittances, measured emittances as function of the branch intensity. This is the horizontal one, and this is vertical. So you can see very clear increase as intensity increased. Then there are actually 3 lines from calculation of intra-beam scattering, assuming the different vertical emittance. So this is the same vertical emittance. Because small vertical emittance means the high particle density, then it means strong intra-beam scattering, then the emittance growth will become higher for smaller vertical emittance. So, and also from this, the measurement is not very accurate, but I can say that at low intensity, because our target is here, so we achieved our target value. But we should improve this measurement, vertical emittance. Okay. Okay. The effect of intra-beam scattering can be also shown as energy spread as function of the bunch population, like this, even clearer. Then, because we have high particle density, or it means small emittance, and relatively low energy, the intrabeam scattering is very strong. And because theoretical calculation of the this effect is ambiguous, and also it depends on the vertical emittance, what emittance we assume, and actually which has not been measured very accurately. So we need more experimental data to answer if we can trust the calculations and if we can calculate the future, the emittance of the future damping wings. So, okay, let me show the normalized emittances of linear colliders. The horizontal normalized emittance and vertical emittance. This is SLC, and ATF at high intensity is here. And at low intensity, we achieve the JLC NLC design. Tesla here and click here. So it's very close to the design. Okay. At ATF, we have a lot of program to test the instrumentation. Let me show one example. This is laser wire monitor in damping wing. We use wire scanner monitors to measure the beam profile. But if you put solid wire in a wing accelerator, then the wire will destroy the beam, or the beam will destroy the wire. Then we cannot use this solid wire, so we developed a laser wire monitor. It's the Y shown here, and beam comes here. Then the thin horizontal wire is created by optical cavities, which consist of two mirrors with laser here. Then when the electron hits the wire, light wire, then the gamma ray will produce, and here is the gamma detector. Then this system can be movable, so you can measure the beam profile. Okay. So this is the example of one example of laser wire scanning. This shows that signal weight as function of table position. So in this case, the Gaussian fit says the sigma is 10.2 micron. And we know that size of the laser wire. Then we can calculate the size of the beam itself. Then from the optics of the electron beam, we can calculate the vertical emittance. In this case, the normalized emittance was 2.3, where our target is 3 times 10 to the minus 8. So it's lower than our target in this case. Okay. Let me show another instrumentation for, in this case, multi-bunch, for multi-bunch operation. This shows the signal from the, in this case, tungsten wire scanner. It is in the extraction line. And we used the air Cherenkov counter to detect the gamma rays from the wire scanner with the avalanche photodiode. And we recorded the signal using 10 gigahertz sampling scope. Then if you plot the, each peak corresponds to each bunch. So if you plot the amplitude of the signal as function of wire positions and the timing or bunch number, then you will get the beam profile or projected profile of each bunch. Then we have 5 wire scanners at different positions in the extraction line. So we, for example, we got this kind of profiles for, in this case, about 18 bunches. Then from this, we can calculate the emittances of each bunch. This is an example of result. Horizontal emittance of each bunch and the vertical. Then again, the horizontal is a little higher than calculated one. Maybe from intrabeam scattering, but we don't know exactly. And vertical emittance was still much bigger than our target. So we have to work on the emittance of multi-bunch beam. Okay. Let me make short summary of ATF. For the single bunch low emittance, we achieved our target at low intensity, but we observed strong intensity dependence from which should be from intrabeam scattering. It is consistent with calculation, but we still need more experimental data or improve the accuracy of the measurement. For multi-bunch, we have developed or been developing the instrumentation. We have still need a lot of work for this, and also emittance intensity stability. So near future plan is like this. We are now doing beam-based alignment of the magnets in the damping ring for lower vertical emittance. And we need to improve laser wire monitor or SR monitor or some kind of beam size monitors. And I added the intrabeam scattering study here. Then for multi-bunch, there are many items of instrumentations, beam position monitors, or beam size monitors, for example, detectors for wire scanners. It needs a very fast electronics to distinguish each bunch. And also, kicker should be tested. And we have other R&D, for example, photocathode RF gun. We already tested in this last summer, but we will restart the test in this summer again. Then now we are almost ready to test the X-ray synchrotron radiation monitor. Now we use the visible light, but X-ray monitor can be more accurate than normal one. So it will. Then there are other projects like optical transition radiation monitor, optical diffraction radiation monitor for beam size measuring, and also we're doing polarized positron production test in the extraction line. So that's all I have. Thank you.
Thank you very much for that clear overview, Hitoshi.
Yes, sir. So what is the prospect of actually getting the emittance? Emittance lower than for the multi-bunch case?
Okay. Actually, now for multi-bunch operation, we are concentrated on the instrumentation, not on the beam tuning or ring tuning. So, how to say? Alpha just started, so it will be improved, I think. I hope.
Are there any plans at the moment to do anything? Are there any plans at the moment to do anything about the Shintake monitor and taking that technology further forward? That's the standing wave interference monitor to measure beam spot size.
At ATF? No. Anyway, I don't know anyways, but at ATF, at least at the ATF, we don't have any plans. I think it's already established, and don't worry, I think.
Yes.
As you mentioned, interbeam scattering is an important effect at the final focus. I want to ask you, what did you mean when you said that the theoretical calculations were ambiguous?
Maybe you should repeat the question. It's not clear that got repeated.
You earlier said that the theory of interbeam scattering, the calculations at least, were ambiguous.
Okay.
I was surprised at that.
Calculation of interbeam scattering is ambiguous.
Why?
Why? Okay.
It's a well-known theory.
Okay. Scattering with the two particles, it's a Coulomb scattering or Miller scattering. So it's very well known. But the cross-section, if you calculate the cross-section, of course it's divergent. So we need some kind of cutoff to get some realistic results. So actually, how to set the cutoff is ambiguous. So they are actually very complicated.
Are there any other questions or comments? Yes.
Do you remember at what gradient the piezoelectric compensation was done that you showed? Do you know what how high they went? You gave the frequency, but shift. But what was the gradient in the cavity?
I can compare with this and this. This and this. So I guess this is about 25. This is about 400 without compensation. Then, yeah, this is about 25. Okay.
Is there any comment? That seems. Oh, Michael Peskin.
Sorry. I was surprised to hear that you were operating the ATF with the wigglers off. I thought they were an essential component to get the final design goal. What is the problem there?
How to answer? But I guess the design of the wiggler was not very good. If you turn on, and we need a lot of work to make a stable operation or good, or make the good orbit. Yeah, I agree that we should do that, and we will do, I think. I promise. But presently, or in the past, we have concentrated on the low emittance without wiggler.
Oh, Michael has a follow-up.
Should we be worried about a damping ring that depends entirely on wigglers, like the straight Tesla damping ring? Or that's a whole nother issue, which is outside of this?
Outside of what?
I mean, is this experience relevant to thinking about the Tesla damping ring, which depends entirely on wigglers?
Experience of ATF, you mean? Difficult. I guess it's not much we can say about Tesla type dampening from the experiments of ATF, but I'm not sure.
Okay, I don't see any other urgent comments, so let's thank Kubo-san again.